Greetings everybody. This is the fourth video for the first practice test for Exam 2. And the other problems deal with uniform circular motion. So that's why I'm doing, the next couple of videos will deal with UCM problems. Here's problem 2 on the test. And it's a sketch of an amusement park ride called the Gravitron. I'm sure you've all heard of it. Whether or not you've actually been on one or not, I'm sure you've all heard of it. And typically it's a large vertical cylinder that spins about an axis fast enough so that the person riding the Gravitron, they drop the floor away, and you're held up against the wall due to the centripetal force. Well, let's assume that the coefficient of static friction between the person and the wall of the Gravitron, because they're clearly pushed up against the wall of the Gravitron, so they're in contact with it. The coefficient of static friction is μs, and the radius of the cylinder is r. Okay, part A. Suppose r is 4 meters, and the minimum coefficient necessary to, the minimum required coefficient is μs is equal to 0.4. We want to find in part A the maximum period of the Gravitron, T max, required to keep the person from falling. What that means is, remember, the period by definition, it's the time for the Gravitron to undergo one complete circle or one complete revolution. Well, so that the period T max T, that's the time for one revolution. The longer the period, in other words, the longer it takes for the Gravitron to rotate, that's meaning the slower it's spinning. The larger the period means the slower the Gravitron is spinning. If it spins too slowly, i.e. if the period gets too large, then the riders will no longer be held up against the wall and they'll begin to slip down. So I want to know what is the maximum period, the maximum period of revolution for this Gravitron, so that the person won't fall. Then parts B, C, and D. Part B, what is the source of the centripetal, i.e. radial force acting on the riders? How many revolutions per minute does the Gravitron make? And what happens if the period exceeds the maximum period? What if T is greater than T max? What will happen? Okay, well let's look at, so this is a UCM problem, because as the Gravitron rotates, the rider is moving in a horizontal circle. The rider is undergoing UCM. So let's go ahead and draw all the forces acting on the rider, apply Newton's second law to the rider, then some knowledge about UCM that we'll need to know. Let's bring up the solution. Okay, this was done in another problem. Okay, here's the Gravitron problem. Now, here's the person in the Gravitron. What three forces are acting on the person? Well, there's the person's weight, mg, in the negative y direction. There's the static friction force, Fs. Why is it static? Well, when the Gravitron spins and the riders get held up against the wall, they're not moving. So it can't be kinetic friction, it has to be static friction. But if gravity wants to pull the person in the negative y, Fs must act in the positive y. So I have Fs and mg. Now remember, the person is held up against the wall of the Gravitron, meaning the person is in contact with the wall of the Gravitron. Well, the wall of the Gravitron right here must exert a normal force on the person, indicated by my Fn. Clearly that green vector, if we zoom in, that green vector representing Fn, I've taken great care. You can see it's clearly perpendicular to the wall of the Gravitron. And it is the force, it's the force of the wall of the Gravitron pushing on the person. And again, so that's just clearly my Fn, clearly makes a 90-degree angle with the wall of the Gravitron. And notice, where is Fn directed? It's directed towards the center because this person's moving in this horizontal circle. You know, I could have drawn this person, you know, I could have drawn him on the other side of the gravitron. Now, I could have drawn the person on, if you're facing the page, on the right side of the gravitron. Well, that doesn't change Fs and mg. Notice in this case, Fn is pointing in the negative x, but that doesn't matter. In each case, Fn is pointing towards the center of this circular motion. So here's the person in the gravitron. Those are the three forces. So let me apply Newton's second law in the y direction, meaning I have, well, remember the person is not accelerating in the y direction. He's held stationary. So Fs must equal mg. Then I'm going to apply Newton's second law in the centripetal, i.e. in the radial direction. Okay, so in the y direction, Newton's second law gives me Fs equals mg. Not complicated. There are only two forces acting in the y direction. The rider is not accelerating in the y direction, therefore Fs has to equal mg. That's equation 1. Well, now in the radial direction, in other words, the sum of the forces in the radial direction, towards the center is positive, away from the center is negative. Well, there's only one radial force, and it's Fn, and it is directed towards the center of the gravitron. So in terms of UCM, it's positive. So Newton's second law for UCM gives me Fn, and what is it? The sum of the forces in the radial direction equals m v squared over r. The mass of the person, m, times v squared divided by the radius, which we're calling large r, the radius of the gravitron, i.e. the radius of the UCM. So I have equations 1 and 2. Fs is equal to mg, and Fn is equal to mv squared over r. Now I need to somehow get the period out of these two equations. So we have to do a little bit more algebra. But first, let me go ahead and let me take equation 2 and divide equation 2 by equation 1. So I'm dividing the left hand, I'm taking Fn and dividing it by Fs right here, because I'm taking equation 2 and dividing equation 2 by equation 1. So I have Fn over Fs, which I know is 1 over the coefficient, because in general mus is Fs over Fn. So Fn over Fs is 1 over the coefficient. Then I'm dividing mv squared over r. I'm dividing that by mg. So when I divide on the right, when I take 2 divided by 1, the m's cancel and I get v squared over gr. So I get v squared over gr is going to equal Fn over Fs, which is 1 over the coefficient. So I get v squared over gr is equal to, I'm going to get v squared over gr is equal to 1 over the coefficient. Well, remember, for circular motion, what is v? Well, v is just your speed. It's just distance over time. But remember, the period is the period of the revolution is the time it takes for the graviton to circle once. It's the time it takes for the gravitron to do one complete circle, or one complete revolution. So the distance is simply 2 pi r. The circumference of that circle, that's the distance, and the time for that one circle is the large t. So v is just 2 pi r over t. Well, I want v squared, because notice here when I divided equation 2, when I took equation 2 divided by equation 1, I ended up with v squared over gr equals 1 over mus. So I don't want v, I want v squared in the green. Well, just square numerator and denominator. So v squared is 4 pi squared r squared over t squared. And I'm going to substitute this expression in for v squared. See that? Right there. Okay? And I need to rearrange this equation and solve for t. So you get on the left hand side, you end up with 4 pi squared r over gt squared equals 1 over mu s. This gives t squared is equal to 4 pi squared r mu s all over g. You can do the simple algebra to go from this step to this one. That shouldn't be difficult at all. Then I don't want t squared, I want t. So just square root each side. So t is root 4 pi squared r mu s all over g. 4 and pi, you know, r was given as 4 meters. The coefficient was given as 0.4. Plug in the numbers and you get a maximum period of 2.54 seconds. So if for a period of larger, so if it takes longer than 2.54 seconds to do one revolution, that means it's rotating too slowly, the rider will slip out. Okay, but that's, so, you know, look at these. Remember, I took equation 2 and divided it by equation 1. You could probably go the other way. You could do 1 divided by 2. You'll get, if you do that, you'll get Fs over Fn, which equals mu s, is equal to gr over v squared. You could do either one. In fact, a good way to work this problem would be, you know, when you set it up, then take equation 1 and divide equation 1 by equation 2. On the left-hand side, you'll have Fs divided by Fn, which is mu s. And on the right-hand side, you'll have mg divided by mv squared over r, which is going to give you gr over v squared. So I mean, and then replace v, or excuse me, replace v squared with 4 pi squared r squared over t squared. To be able to do it either way and do the algebra, but remember, you want an expression for t. You want that maximum period of revolution. You get 2.54 seconds. Now, how many revolutions per minute? Because we want to think of it, you know, more in per minute, you know, RPMs. So how many revolutions per minute does it make? We'll just do a simple conversion. Oh wait, I'm sorry, I skipped B. Let me go back to part B. What is the source of the centripetal force acting on the riders? Well, look at your figure. Of those 3 forces, what's the only one that's pointing towards the center of the gravitron? I.e. centripetal, radial means the exact same thing. Well, Fn. So Fn is the centripetal force, right there. Okay, part C. I just want to convert revs per second. I want to just take the period and convert it from revolutions per second to revs per minute. The period, remember, if the period is 2.54 seconds, if t is 2.54 seconds, that means it's making one revolution in 2.54 seconds. Remember, the t, large T, is the time for one revolution. So if t is 2.54 seconds, it means it's doing one revolution for every 2.54 seconds. Convert that to revs per minute. Nothing complicated. There's the conversion right there. It's making 23.6 revolutions per minute, fairly fast. Now, part D, what happens to the riders if the period, if t is greater than t max, if it exceeds 2.54 seconds? Well, what if that happens? Then mg will become greater than fs. If t is greater than t max, mg becomes greater than fs. And then the riders will slip down. That's the whole idea. The gravitron has to have it rotate at a certain minimum speed. Anything slower than that minimum speed will result in the rider slipping down. Remember, the larger the period means the slower it's rotating. The larger the period, meaning it's taking longer to do one revolution. So the larger the period, so there's only, so you can't exceed that maximum period of 2.54 seconds for a gravitron of these dimensions right here. All right, let me save this video and get it posted.